So thank you everyone for joining this webinar. It's a great pleasure to have Dr. Xinwei Wang from Queen Mary University of London in UK. I'll speak a bit about his profile. So he's a lecturer at the Queen Mary University. He used to be a postdoctoral at the same university, but also at the Delft University of Technology in Netherlands. He obtained his PhD from Beihang University in China. His research interest lies in the areas of artificial intelligence and machine learning, operational research, with applications in decision support and risk assessment systems. But also he has a great interest in aerospace and transport systems. He is an associate editor of the journal Advances in Space Research, and he's a recipient of the Marie Curie Fellowship. Dr. Wang has authored over 40 publications in high-quality research, and today he will give us a talk about the Agile satellite systems scheduling, which is, I think, is a great topic for a collaboration and also for our interests. So please, the floor is yours. You can share your screen and. Great.
Thank you for your kind introduction. Can you see my screen now?
Yeah, we can see your screen. So make it full screen.
Yeah.
Yeah, now it's perfect. Yeah.
Okay. Yeah. Thank you for your kind introduction and having me here online for the webinar. Good afternoon, everyone. I'm very happy to have this opportunity to introduce a research topic for Agile Earth observation satellite scheduling. As this may be a relatively new topic to the audience, today I will give you more like a tutorial of Agile satellite scheduling in terms of formulations, methods, and future directions. A quick introduction to Queen Mary University of London, where I'm now working. So Queen Mary is a distinguished member of the Russell Group of British research universities. This can be also reflected from its decent global university rankings. In the native UK Research Excellence Framework, Queen Mary's engineering secured an impressive 7th position, and its research publications got a remarkable 2nd place. In addition, Queen Mary is the only campus-based Russell Group University in London. As you can see from the left figure, it takes no less than 20 minutes from Queen Mary's main campus to the city center of London. Yeah, also introduction of my background. Yeah, I think I can skip this slide. Mikan is already introduced my research background. But anyway, I have worked in several different areas. For instance, I designed the various routing and scheduling algorithms for airport aircraft ground movement to improve the airport operations efficiency. I have also applied data-driven models to assess driving risk between automatic vehicles and proposed risk-aware motion planning methods. Another major stream for my research is space systems, and it has been applied to Earth observation and on-orbit surveying as well. Today, in this talk, I will mainly talk about the Agile Earth observation satellite scheduling problem. There is a clearly increasing trend for the satellite Earth observation activities. From the report in the left, the Earth observation global market is one of the most dynamic and promising sectors, and it has been predicted to be doubled from 2020 to 2030. On the other hand, the Earth observation satellite and the rocket launching techniques have been well developed in the last 10 years, and we have seen more and more satellite constellations on orbit since 2014. It also raises a challenge on the satellite operations management. Let's take a closer look at the Earth observation system. I will give you an example how it works. The Earth observation user or the system operator will first determine some target areas to be observed. Then the system will make a schedule and upload a corresponding command to a selected satellite. After receiving the Earth observation command, the satellite will prepare and execute the observation task within a specific time window, and the collected images will then be transferred to either the relay communication satellite or directly to the ground receiving station. Now the images are on the ground and we can start data processing and provide necessary information to the user. Therefore, naturally, we can divide the system into two components. When the images have been on the ground, we have an imaging processing component to process and analyze the data. I believe this could be the main research focuses in your EXCELSIOR project. And the other component is for the space systems, and in this case, specific for satellite scheduling. That is to say, suppose we have multiple satellites and a set of targets to be observed, we need to determine at which time we need to observe which targets. So we are going to address this problem in the next half an hour. Here is the agenda. I will formally introduce the Agile satellite scheduling problem and give you a little bit math formulations and some general methods to solve the problem. I will also introduce one of our recent works on satellite scheduling. In the end, I will point out some future directions. For your information, the majority of today's talk is based on our review paper published in the IEEE Systems Journal. I will start with the term Agile. The keyword Agile is actually to indicate the advanced attitude ability for the Earth observation satellite. As we can see from the left figure, the arrow indicates the satellite flying direction, and the two satellite icons here indicate the satellite positions at different times, TA and TB, respectively. So for a traditional non-agile satellite, when it observes the ground target, it needs to rotate its roll angle here for a suitable observation field of view, and it can only start the observation at a fixed timing, TA, and end the observation at time, TB. This is because the non-agile satellite cannot adjust its attitude as it wanted. Although it has some flexibility along the roll axis to cover the ground target, but the satellite cannot adjust its pitch angle to look up or look back, allow the satellite to start the observation time before time A here. That is to say, as we can see in the right, the non-agile satellite can only observe either target 1 or target 2 if there are time conflicts between the two targets. It's the same for the target 3 and 4 when their visible time windows have some overlap. So we only have to schedule one task for either task 3 and 4. Thanks to the satellite technology development, the Agile satellites have been developed and launched in the past 10 years. So different from the traditional non-Agile satellites, the Agile satellites now can rotate its pitch angle. That means it can observe the target now have the larger visible time windows, and now we can look up or look back to start the observation time with the different observation time here. So as we can have a comparison in the right, now the satellite, the Agile one, can first observe the target 1 by looking up its pitch angle here, and then look back to observe target 2. So clearly, the observation efficiency can be significantly improved thanks to the agile ability. However, it also makes the problem more complicated because we not only need to select the targets to be observed, but also we need to determine an exact time observation interval as shown here. So this motivated us to investigate the agile satellite scheduling problem. Suppose we have a set of agile Earth observation satellites and a set of targets to be observed. We aim to select and schedule observation tasks to maximize the entire observation profit while satisfying operational constraints. Notice that now we have infinite solutions to an even very small AEOSSP, because the observation start time for a target can be any value within a visible time window. Another thing to clarify is that in the AEOSSP, we don't explicitly consider the data download scheduling problem. In principle, we also need to similarly schedule the data download tasks between satellite and ground station. This is because the AEOSSP is already very difficult to solve, and we would like to decompose these two scheduling problems. Instead, in the AEOSSP, we will model imaging data capacity as one of the operational constraints, which we are going to introduce later. Well, to the best of our knowledge, the first paper to address the AEOSSP was published since 1997, and almost half of the reviewed articles have been published in 2018 and 19 when we conducted the literature review in 2019. We can also observe a similar trend from a recent review paper, which covers all kinds of satellite scheduling problems. Indeed, as we can see, the number of papers has significantly increased in recent years, and much more attention has been attracted to the satellite scheduling problem. It's also worth mentioning that the AEOSSP is a multidisciplinary research problem, and it has attracted researchers from different areas. So in a practical view, the AEOSSP is a space system engineering problem. But from a theoretical point, the AEOSSP can also be viewed as a combinatorial optimization problem involving various modeling methods and solution techniques. The AEOSSP can also be regarded as an application of remote sensing. Researchers in different areas contributed to the same topic, and this makes the problem being of great value both in practice and theory. Now we are going to mathematically formulate the problem. I will start with two basic formulations and discuss two commonly considered operational constraints to make the problem more practical. I will also introduce three typical variations of the problem. So first, we are going to introduce a time continuous formulation of the problem. Suppose we have a set of satellites A, S, and a set of ground targets T. We aim to maximize the entire observation profit as defined in the object function here, where though I is the profit for each observation target, and Xijk here is the Boolean decision variables to indicate if we select the task to observe the target, and Tijk is the continuous variable to decide the exact observation start time. This is why we call the model time continuous. There are three subscripts for the decision variables. It indicates that the target number the relevant satellite J and the number of circles for the satellite. This is because when one satellite makes a circle along the Earth, the satellite had the most one visible time window to one target. So in literature, it's commonly used to set a decision variable X for each respective satellite circle to each target. There are three constraints considered in the model. First, we need to restrict the number of observations for one single target. Normally, the threshold here, Ni, can be set as 1, but sometimes we could also use another big number to consider multiple observations for a single target. In addition, we need to make sure the scheduled observation interval should be within the visible time window, which is the input for the model. And the last constraint is that we have to ensure the current observation start time plus the observation duration, which is the constant in the model, then plus the attitude transition time should be less than the start time for the next observation task. Since we could have different attitude to look up or look back to observe a target, so here the task transition time delta t is nonlinear. This is the major reason to make the time continuous model difficult to solve. To address the nonlinear issue in the time continuous model, we proposed another type of model, the time discrete one. So in this model, we first discretize the visible time windows into multiple tasks for the same target, and each candidate target, each candidate task now has a determined observation interval. That means we are now only need to select one of the discretized candidate tasks, and their observation interval has been fixed already. So that's why we only need one group of decision variables in the time discrete model X, J, K, P, Q to indicate that if task Q is a direct successive task P in the circle K for satellite J. So in the model, we also have similar constraint for the number of observations and a new flow constraint for the decision variable. So this is the standard constraint for a flow variable. It means that if task P has been selected, it will definitely have one precursive and one successive task. However, seems like the task transition constraint is missing here. Actually, the task transition constraint has been considered and checked when we generate the decision variable here. The decision variable will only be defined when the transition constraint between P and Q is satisfied here. So this can clearly reduce the formulation size, but requires extra pre-processing time. So in terms of the operational constraints, given the satellite onboard resource limitations, the energy and the data storage capacities are critical to the performance of the remote sensing system. So the onboard energy availability is partially supported by a solar panel connecting energy from the sun. Although the conditions of the solar energy connection change due to space environment, the amount of the energy connection in one satellite circle is assumed to be nearly constant. So this is also part of the reason why we relate the observation task with different satellite circles in the model. So we assume that the maximum energy capacity for one satellite circle is a constant, and the unit time imaging and maneuvering energy consumption are defined. In this way, the number of observation tasks in each circle can be restricted in this constraint. Then the memory constraint can be considered similarly because we assume that for each circle, the satellite will have chance to transfer data to the communication relay satellite or to the ground station. Well, the AEOSSP has been well studied over the past 20 years. So the problem itself has been further extended and modified from the basic model we have just introduced. Here, I'm going to introduce 3 more variations of the satellite scheduling model. For instance, for some targets, it may be relatively large and the satellite cannot completely observe the target in one image. So this is what we can see in the left figure. An area target now is divided into smaller strips, and the observation profit of the area target can now be represented by a nonlinear function as shown here. On the other hand, a point target could also be desirable to be observed more than once, such as for environmental assessment. Such kind of multi-observation for the same target can help achieve stereo or time series observations, and the observation profit then becomes nonlinear as well, associated with the observation count for the same target. So the original objective function in the formulation is to maximize the entire observation profit or to maximize the scheduled number of targets when the target profit is equal. However, multiple goals from different users may need to be considered in the scheduling problem. As far as we know, this is the first work to introduce multiple objectives into the AEOSSP. So in this work, the authors proposed a multi-user AEOSSP where the users are interested in different observation targets. So to address the fairness between different users, they established a multi-objective model aiming to maximize the scheduled observation profit and at the same time minimize the profit difference between each pair of the users at the same time. In another paper, 3 objectives including profit, quality, and timeliness are considered. So the first objective is to maximize the observation profit, and the second one aims to maximize the average quality of the observation tasks, which could be related to the observation angle. And the last one relies on when the target is observed. So the last variation of the problem is the autonomous model. Currently, most of the satellites now are entirely controlled and scheduled from a ground operation center. However, this cannot ensure the success of the scheduled observation tasks because of some uncertainties, for instance, because of cloud coverage. Then the autonomous model can take incoming events and information into consideration in a dynamic manner. So as we can see from this figure, in the last horizon, the satellite completed the observation for target 3 and have scheduled tasks for targets 7, 9, and 6. Then once the satellite receives the latest information for new target 4 as a trigger, the satellite moves to the current horizon. The satellite will first execute the previously scheduled task for target 7 and then reschedule tasks considering the new target 4. The satellite will then execute the rescheduled tasks and move to the new horizon when there is new information coming. Well, a short summary for the AEOSSP formulations. As we can see from this table, most of the research is based on the time continuous model, and only a limited number of works used the time discrete model. A number of studies have addressed the complex operational constraints since they are of great importance for practical satellite scheduling. Also, multiple objectives have received much attention recently, and the autonomous scheduling is also promising for engineering practice. Well, next I will talk about some typical solution methods to solve the proposed scheduling problem. We can classify the methods into 4 categories, as we can see from the table, including exact method, heuristic, meta-heuristic, and machine learning. So because of time limit, I will provide a quick overview in terms of different methods. I refer you to our review paper if you are interested in more details regarding the methods. So currently, heuristic scheduling is widely used for the AEOSSP, but typically fail to provide bounds on the quality of the solution. So to address this issue, 2 exact methods, the branch and bound and the mixed integer linear programming model with commercial solvers have been developed. The pros and cons of the methods are evident. On one hand, the exact method is able to provide an estimate of the potential best solution value, and therefore the obtained solution can be proved to be either linear optimal or optimal. However, these methods can be time-consuming and only applicable to some small-scale instances. So this is also a reflection of the no free lunch principle. You have to keep a balance between the solution quality and efficiency. In terms of the heuristic, these methods can be used to speed up the process of finding a satisfactory solution. Basically, these methods are specifically designed for the scheduling problem, and they are easily we can easily implement these methods. So you can design the selection rules by your own using either greedy rules, conceptual framework, and any defined priorities as you want. However, there's no guarantee of the solution quality, and the users need to construct a new heuristic when the problem has been slightly changed. As for the meta-heuristic, it's a higher level procedure to find, generate, and select a search algorithm which can provide a high quality solution to an optimization problem. So according to the reviewed literature, meta-heuristics contributed to the majority of the solution methods in the satellite scheduling problem. So we can typically divide the meta-heuristic into 2 categories, the evolutionary algorithm and the single point search algorithm. Evolutionary algorithm can mimic biological mechanisms such as mutation, recombination, and natural selection to find an optimal design. So it includes genetic algorithm and colony optimization, where there is a population inside the algorithm to evolve for a high quality solution. So it's particularly effective for the multi-objective AEOSSP. And contrary to the population-based evolutionary algorithm, the single-point meta-heuristic uses a single potential solution called a point to explore the search space. For instance, TURB search uses a TURB list to prevent the algorithm from revisiting a solution that has been explored. And in local search, we can design different operators to effectively explore the solution space and in the end find a high quality solution. However, there are also some limitations for meta-heuristic. One major constraint is that the meta-heuristic could have different performance in different parameter settings, and the performance could be not stable with different numbers of satellites and targets to be observed. So the last type of method is machine learning. Up to 2019, there are only 3 papers using machine learning to address the problem. However, in the past several years, machine learning has been an emerging technique, not only for the satellite scheduling problem, but also for all optimization problem. I will further discuss this as one of our future directions later. So before we move to the future direction, I will briefly introduce one of our recent works, a satellite scheduling chance constraint programming model to address the cloud coverage uncertainties. The motivation is straightforward. So the cloud coverage has a huge impact on remote sensing, especially for optical sensors. So for a scheduled task, we could gain no profit because of the cloud coverage. So that motivated us to propose a chance constraint programming model. In this model, we define if a task could be successfully observed as a random event, and there is a success probability VPK for each task P in the satellite circle K. So we also assume that the cloud cover remains unchanged during we execute the task. This can be demonstrated from the dynamic cloud images, where we can see the cloud typically don't change too much within a small duration. Then we can redefine the objective function as f, and subject to a new chance constraint. So here, the constraint indicates that the probability of the event where scheduled tasks will gain profit no less than f is greater than a confidence level defined as 1 minus gamma alpha. Before we move on, I think we need to first address the question here. Why not we directly maximize the entire profit expectation? We can answer this question with this toy case. So suppose we have 2 tasks and they conflict with each other, and we need to select only one to observe. Given the provided information from the table, if we aim to optimize the profit expectation, then we need to select target 1 because its profit expectation is 10, which is greater than 9 for task 2. However, if we use the proposed CCP model and use confidence level, say 0.8, then the profit is 0 with the probability 90% for target 1. And for the task 2, the profit now is 10 with the probability 90%, and the objective then should be 10. Therefore, under the CCP model, we need to select task 2. So selecting task 2 actually could be more reasonable because we know we will gain more profit with a 90% probability in this case. So this is why we have introduced the CCP model rather than a simple expectation model to address the cloud coverage uncertainty. Then let's go back to the CCP model. Now the question is that how we can calculate the CCP uncertain observation profit. Suppose we have scheduled 4 tasks here to observe. Then to calculate the profit, we can enumerate all the potential 16 combinations and calculate the respective probabilities. So in this case, we can then obtain the objective function value f. However, in practice, we could need to schedule hundreds and thousands of targets. So in this case, we will need to sample the all possible combinations using Monte Carlo simulation and generate a set of scenarios as to calculate the CCP profit. So then we proposed a heuristic to solve the CCP model. In this algorithm framework, we first generate some initial solutions by using selection rules, and then employed a fast insertion algorithm to determine the exact observation interval for each scheduled task. Then we can use the introduced sample approximation method to evaluate the uncertain observation profit. Here, an improved simulated annealing algorithm was incorporated to further improve the solution quality. So to validate the proposed model and the method, we simulated a one-day scenario with 4 agile satellites. We considered different number of targets with different distribution. The parameter settings and the real-life target distribution are also provided here. So as an improved simulated annealing algorithm is designed, we first need to test its hyperparameters, the disturbance rate for new solution generation, and the iteration number to find a better solution. Comprehensive experiments have been conducted, and we conclude that the algorithm performance is quite stable in terms of different settings, as we can see from this figure. Therefore, we selected a small value for the iteration number to reduce the runtime for the remaining simulations. Then we consider different combinations of the satellite energy and the data capacity parameters for the 4 different scenarios. As shown from this figure, we conclude that the profits indeed are increased with larger energy and data capacities, which is reasonable. And also we observe that the algorithm running time is stable regardless of the different constraint settings. So in the end, we report the comparison results between the proposed algorithm and the state-of-the-art. By comparing with other 4 existing algorithms, we can conclude that our proposed method, the ISA, is demonstrated has the least running time, and this can also be reflected from the algorithm complexity analysis in the table. So more importantly, the proposed algorithm indeed gained the overall highest profit across different scenarios. Well, now we are going to the final part to point out some future directions for the AEOSSP. So first of all, in the AEOSSP formulation, the data download process is not explicitly considered, as we mentioned, but yeah, it's indeed essential for receiving the final observation data and image in practice. So we have mentioned that separately schedule the observation and the data download task could be a natural choice because the problem is already very difficult, and a fully integrated model could be quite intractable. So, but anyway, in this case, I believe it's promising to present the practical engineering system using an integrated model. But in this case, an efficient scheduling method needs to be carefully designed. Another potential direction is for coordinated scheduling. So the agile satellites already have a larger attitude maneuverability, but still the observation can only be done within specific time windows. Therefore, it's necessary to consider coordinating other observation resources, for instance, including the UAVs and airships, to enhance the overall system observation efficiency. As a first step in one of our recent works, a hierarchical framework has been designed to realize the coordinated Earth observation scheduling. Well, as the boost of machine learning and AI in recent years, clearly it's also promising to apply them into the site-wide scheduling problem. However, one major limitation is that the obtained solution from AI could be hard to interpret and explain. So in our latest work, we have tried to combine a genetic algorithm with a deep Q network to address this issue. So on one hand, the genetic algorithm can explain how the solution performance is gradually increased. And on the other hand, the deep Q network was applied to help generate better initial solutions, as well as to improve the efficiency of the local search. So this work can serve as a baseline for future exploration. Another pioneering work I would like to introduce is using a large language model for explainable site-wide scheduling. By designing an end-to-end site-wide scheduling framework, this work has explored how an AI language model can be trained and applied to generate a scheduling solution as well as proper explanations. So this work is rather premature, but opens a new direction to the use of AI for space applications. So the last direction I would like to mention is to incorporate new observation needs for the scheduling mode. As the site-wide technology further develops, now we have a so-called super AEOS, which can complete more complicated observation tasks, including the non-parallel ground track, the active push broom, and the non-linear trajectory observation. As discussed in a recent paper, so clearly such kind of super AEOS site-wide can further improve the scheduling efficiency for a large area target, and it also increased the scheduling complexity at the same time. I'm also particularly interested in what could be your new observation needs from the remote sensing perspective. For instance, so is there an advanced way to observe the target to generate a stereo and time series observation images? I look forward to a discussion with you all during the Q&A session. Thank you for your attention.
Okay, thank you, Xinwei, for showing your research. Any questions from the audience? Okay, so I have some questions. So you for your future directions, you spoke about integrated scheduling. So integrated scheduling, you mean on board on the satellite?
Yeah, you mean for this slide?
Yes.
Yeah, so in this case, what I mean is that we need to consider both the observation and the data download scheduling problem together to make the scheduling problem integrated. And in this direction, we only focus on the satellite.
Okay. So I thought so will this will affect the energy constraint from my understanding, if you consider this, isn't it? So regarding the energy constraint of the satellites, so the capacity, okay, I understand is fixed. What about the energy consumption? Is it fixed or is it non-linear? Is varying?
Well, that's a very nice question. So to be honest, of course, if we want to model the site-wide energy consumption more realistic, of course, we need to build a more complicated and nonlinear model. But to simplify the model, at least in the basic model, we basically use a unit time consumption constant to reflect the energy consumption. And in that case, yeah, indeed, we made a very simplified energy consumption model, directly consider a linear increase energy cost. But I think it's worth to also investigating how the real energy consumption model can impact the solution. Because on one hand, we need to make the model easy to solve, and on the other hand, we need to ensure the model should be realistic as much as possible. So we need to strike a balance between them. And from my point of view, I think it would be ideal to start with a basic and simple solution, model, and then we can check if the generated solution can well match to the real world cases when we have a non-linear and complicated energy consumption model. And then we may try to then further expand the complexity of the energy model and then rerun the model by using probably different algorithms. Then we make it as a loop iteration to check, so to what extent should be the best energy consumption model in satellite scheduling.
I mean, I totally agree that the model should be simplified at the beginning and then built on that. I totally agree. So I mean, I think that the energy consumption is basically uncertain. So it's similar with electric vehicles, for example, because the energy consumption there, we assume that is fixed on our models, but in reality it's uncertain. It's an uncertain variable.
Yeah, well, I also agree with your statement. Yeah, it's true. But as I mentioned, indeed, we need to keep a balance here.
Yeah.
So yeah, you have to do some you have to sacrifice some efficiency and accuracy of the model itself.
Anyone else? Any questions?
I have a question.
Yes, thank you.
Thank you very much for your presentation. Actually, I am a PhD candidate working with artificial intelligence using Earth observation data, and it's really interesting how machine learning can approach those problems. As far as I know from literature, they have used different deep learning or in general machine learning approaches to solve this problem with data-driven approaches mainly also. And I was looking if it's available any benchmark data set or real life data set that we can use in order to try different algorithms in solving those problems. Because from what I know until now, I haven't found anything, but it's really, really interesting. Try these problems.
Yeah. Yeah, thank you for your question. Yeah, indeed, that's also another potential issue, as I mentioned, how we can use the AI and deep learning to propose a data-driven algorithm to solve the satellite scheduling problem. Yeah, indeed, I have the similar concern about the data, the realistic data. So as far as I understand, as far as I know, there is no publicly open Earth observation scheduling data you could use for training and for training purpose. So what we have done in the previous literature is that we just simply generate a bunch of satellites and targets on the Earth, and then check the time windows by ourselves, right? And then we may use some exact methods to generate a optimal solution by using a very long time. And then in this case, most of the papers just established a benchmark by themselves themselves, and there is no commonly used benchmark. Indeed, that is a pity, because the thing is that the data could be a bit sensitive, because we are working in aerospace engineering. So yeah, we look forward to have a discussion maybe with other space agency, the ESA or the UK Space Agency, to check if they are happy to release some kind of data for us for the Earth observation. So normally, what they have released is image data, but actually the orbit and the actual data could be more sensitive. I guess that's the reason why we so far couldn't have the access to such kind of data.
Okay, thank you very much.
So Xinwei, speaking of benchmarks and instances, so the scenarios that you solved in your papers, those data are available. I mean, we can regenerate the instances and compare with your algorithms if we have an algorithms or no.
Yeah, for sure. But the thing from my side, I am not a good programmer, and I'm not good at managing code. So yeah, indeed, ideally, we need to submit the code to some open platform like GitHub, especially for the benchmark. Then for the coming researchers, they can also employ the benchmark to do comparisons. But unfortunately, we haven't done so. But that should be one of my plan in the future.
Because I was looking for instances so I can start working on this problem, but I couldn't find anything. So I don't know, they don't share the the code.
True, that's true. Yeah,
Okay,
yeah, because yeah.
okay, that should be something that yeah, we need to work on it.
Yeah, because the truth is that so most of the researchers now are from aerospace engineering, and they are not good programmer, and they don't have a good habit to manage the code. I think that's
Well, I mean,
okay.
this is the same thing in computer science. So we have the same problem. Most of them, they don't share their code and they don't share their data. So, but I always share the code of my algorithms because I want others to use it and compare with. So
Yeah, that's
my
great.
point of view. I am a supporter of the open research. So I have one final question. I was wondering how do they manage the schedule at the moment? The scheduling
You mean in real world?
in the real world, yes.
Yeah, so as far as I understand, and I also mentioned in one of the slides, so in fact, at this moment, we don't have the so-called autonomous satellite. So basically, for the scheduling, for the satellite scheduling, we may still use a grounded operation center to generate a schedule globally, and then upload the relevant satellite schedule command, including the observation task as well as the data downloading task to a specific satellite. So I understand this is how the satellite works nowadays. So if I remember correctly, so Stanford launched the first autonomous satellite late last year. So as you can see, that should be the first one, which is openly regarded as autonomous satellite. So in real world, most of the satellites for Earth observation just are controlled by a central, by a ground central center.
Okay, I mean, so okay, I mean the algorithms that they are using, the scheduler, for example, they don't share the knowledge of that, no. They don't share which scheduler are using. So.
No. And
Because I think it would be nice, I mean, to compare what you have with what they have at the moment, you know.
Yeah, in fact, there was a competition regarding Earth observation satellite scheduling, like it's at least 10 or 20 years ago, organized by the French Space Agency. But that was a very long ago for the first Agile satellite launched by the French Space Agency. So in that competition, they released some relevant data, so you may use for a comparison. But anyway, that was already at least 10 years ago.
And perhaps one more question. Regarding for the methodologies, you showed in your literature that you have a lot of metaheuristics and heuristics and so on. Which algorithms from your experience do work best for these problems? Let's say for the multi-objective one.
Well, yeah, if we talk about the multi-objective satellite scheduling problem, definitely the genetic algorithm is the best choice. Because I couldn't remember the name. Yeah, exactly. Exactly. There are a lot of variations sorry, I can't spell the name. There are a lot of variations based on that standard algorithm for multi-objective satellite scheduling problem. So yeah, indeed, genetic algorithm should work the best as far as I know.
From my experience, also mimetic algorithms should work well on these problems. Usually are the state-of-the-art algorithms, because it's a combination of a metaheuristic with a local search. So this is something that I was thinking of, because I mean in other combinatorial problems, mimetic algorithms are probably the best ones. I'm not sure if you are aware of mimetic algorithms.
Yeah. I of course I know the general idea of the mimic algorithm, but myself haven't explored the algorithm yet. Because from my point of view, there are already a bunch of metaheuristics, and as I mentioned, sometimes it's very hard to evaluate their performance because now we don't have a standard benchmark for real comparisons. My personal interest would be thinking about if we can combine the exact method and some heuristic or meta heuristics together, because we may gain some information of the lower bound or the upper bound. In this case, it's the upper bound of the scheduling problem itself by incorporating the information from exact methods. That's something I'm really interested. Because only in this way we may have a quantity guarantee for the generated solutions.
I agree with that. But also, I mean, it would be, as a first step, I think we should discuss more about generating benchmarks and have them publicly available for others to work on it. I think that will be a very good research direction, and the community will benefit from it.
Yeah, I fully agree. That would be a great work.
So yeah, so I managed at some point to have benchmarks on the electric vehicle routing problem, which I formulated with some colleagues, and it went really good. I mean, it had so many researchers were interested on that. So I think we should proceed the same with this problem. Okay, so that's all from me. Later on, I will send you an email so we can further discuss about these things. I don't know if anyone has any other questions before letting Xinwei go.
Hello, Dr. Wang. My
Yes.
name is Sophocles. I recently started working here at ERATOSTHENES, and it seems to have missed the first part of your presentation due to some technical issues. So I was wondering if we could have a copy of your presentation, maybe in PDF, because this seemed to be a lot of information for one session, and I would be very much interested in what you are doing.
Yeah, thank you. No problem. I will send the slide to the organizers.
Okay, that would be great. Thanks.
Okay, so I think this is the end of the webinar. I would like to thank Xinwei Wang for his interesting presentation, and I'm looking forward for further collaboration with you. And so thanks everyone for attending this meeting.
Thank you for thank you for having me here, Mikanis, and thank you all for attending my webinar.
Thank you, Xinwei.
Thank you.
Have a nice day.
Yeah.
Have
Bye.
a nice day. Bye bye. It's time to start.